Hi, I'm Mr. V. This is Illustrative Mathematics, Unit 5, Solid Geometry, and this is our first lesson from this unit. By the end of this lesson, you should be able to say, I can draw a two-dimensional shape that creates a particular three-dimensional solid when rotated around a given axis. And the second is I can take a three-dimensional solid that is a solid of rotation and identify the three-dimensional solid that will occur when I rotate. So for example, if I have a two-dimensional piece of paper here, this is two-dimensional, length and width, and if I rotate it around this axis, what kind of shape is that? Or maybe I did it really, really fast. You can see it. I don't know if you can see it, but it looks like a cylinder. Anyway, that would be what we're going to be doing today. This first page is which one doesn't belong, and this is where you get to exercise your understanding of differences between. So this is not only what do you notice and wonder, but this is how do you compare the two different things. Each one does not belong with the others for a reason. On the next page, I actually give you some student ideas. So some students said this is the only one that can bend or they can move. The others, B doesn't belong because it's the only one that's made out of a solid piece of material. C doesn't belong. Someone tried to say that this is a triangle. This is not a triangle. A triangle is two-dimensional. This is three dimensions. Someone said it's a pyramid. It's not a pyramid. A pyramid does come to a point like this does. This is a cone. And if you were to think of your ice cream cone, your sugar cones, that's a cone shape is the name of it. It's also not the only one that's not a toy. So that's another reason. And finally, D doesn't belong because it's the only one with corners. And this is important. It's the only one that doesn't have an axis of rotation. It keeps it looking the same for all angles, for all degrees of rotation. On the other part that I didn't say was when you do a cross section of this one, part C, you cut it in along a horizontal plane. It's not the same all the way across. Each of these others would be like this would be a circle if you were to cut it. This would be a square, and this would be a circle. This is circles, but they're different size circles. The axis of rotation, though, is what this lesson is about. This is about solids of rotation, and that's where we go. So here we have some formulas for a couple of different shapes. One is a cylinder, and one is a cone. A cylinder looks like this. It looks like a can. It's got the same top and bottom like a prism would. Some people think that this is a prism, but it's not. A cylinder could be thought of like a prism, I guess, which has infinite sides, but prisms have sides and multiply that, but it has the same top and the same bottom. And when we find the volume of this, we take the area of the bottom, which is a circle, and you multiply it by the height. So the area of a circle is pi r squared. To help you remember that, I have a joke, which is to help you remember the area of a circle. This country bumpkin sent his son off to college. And his son come home, and his daddy say, "What did you learn?" He said, "I learned the area of a circle, pi r squared." And his daddy slapped him upside the head and said, "Pi r round, cake r squared." Fine. Pi r squared times the height would be the volume of this. I also have a cone here, and this is a pretty big cone. This is a cone. It comes to a point. Its base is also a circle, and so it's pi r squared. And if you multiply pi r squared times the height, that would be for a cylinder, but we're going to take 1/3 of that to get the volume of this. And later in the lessons in this unit, we will talk about how we came up with that formula, but this is the formula. So for the next 3 pages, there are some assignments to do, and I'm going to work through these with you on my whiteboard. First, let me move this picture over to the side. Let's see. Let's start with this first one. And we're to join the points together. So if you've forgotten how to plot points, 0, 0 is our origin. This is where we will start. And I'll do this right here, 0, 0. We're going to go 0, 2. So 0 in the x direction, 2 in the y direction, 3 in the x direction, 2 in the y direction, and 3, 0. So this would be our points. And we connect them, and it makes this rectangle. To find the area of the rectangle, we'll use the formula for the area of a rectangle. Area is equal to length times width. We'll substitute our values. This is 3, this is 2. So we have 3 times 2, and we get our answers. So we write the formula, we substitute the values, and we solve. This is 6. And this would be units squared because we have a length component and a width component. Units times units is units squared. In the exercise, you were supposed to rotate this first around the x-axis. Now I'm going to show you how to do this. This point is 2 away from the x-axis. Down here will be 2 away. This is 2 away, it'll be 2 away. And I can draw what would be a circle if I was looking at it from the end. From this side, it'll be an oval. From over here, I'll draw it. And since I would not be able to see through the can, I'm going to use a dotted line here. And still, my radius is 3, and my height of this, if you were to turn it sideways, the height would be 3. So we'll write the formula. The volume of a cylinder is equal to the area of the base, which is pi r squared, a circle, times the height. And when we substitute the values, we have pi times 2 squared times 3. This is 4 times 3 is 12. So my answer is 12 pi. 12 pi, and this would be units cubed. Well, why is it units cubed? It's got a length component, a width, and a height. It's got units times units times units. And when it's a volume, it's always going to be units cubed as opposed to units squared, which would be an area. And we can plug this into a calculator to get an answer or approximation. We do 12, and I type in pi for pi, and I get 37.6991. So that rounds to 37.699 units cubed when I do this to 3 decimals. And that's pretty much what we were doing for this exercise. The second part of this, though, is to rotate that same square, that same 3 by 2 square, so this is 3 and 2, around the y-axis. This time when I write the formula, the volume of a cylinder is equal to pi r squared times the height. So we'll substitute the values. Pi, the radius this time is going to be this value, and this is my height. So I have 3 squared times 2. This is 9 times 2, which is 18 pi. And this is in units cubed. Well, wait a minute. 18. The previous one, and I can plug this into the calculator. Let me just do that first. See what this is really going to be. 18 pi is going to be, I need to write this down. 56.54866. 56.8. What is it? 56.54866. If I were to round this to the third decimal, I'll underscore the third decimal place, draw a line to the right of it. If this number is 5 or more, I'll add 1. So this approximates to 56.549 units cubed. Wow. Okay. This is a lot different from what we just had. We had 12 pi and 38, and here we have 18 pi and 57. What's going on here? Why is this so much different? Can you explain it? Well, the big difference is this r squared in my formula. Here the r is 3, and when you square 3, you get 9. Here the r is 2, and when you square 2, you get 4. So there's such a big difference. This is like 1.5 times what the other one was. Our next exercise was to do the same thing, drawing these points and putting them together. So I'll do this. I'll just do this out. I'm doing this for your benefit so that you can see this. 0, 3 is up here, 2 zeros down here, and I get a triangle. And we need to know the area of the triangle. So to do this, I'll multiply the length. That's the area of the triangle. The formula of an area of a triangle is 1/2 times the base times the height. This is a best practice. This is what I want you to do, is to write the formula, then to substitute the values, and then to solve. So this would be 1/2 times 2 times 3. And my answer is 3. And this has got a length component and a width. So this is units squared. Next, we were supposed to rotate this around the x-axis. And again, when we do this, I'll draw my little square. I'm going to go down 3 because I went up 3. and I want to connect this point. So the volume of a cylinder, of a cone, volume of a cone is 1/3 times pi r squared. Let me move my picture here, move this down. 1/3 times pi r squared times the h. So it's pi r squared h, but it's times 1/3 because it goes to a point. It doesn't go straight up. And when we substitute values, we get 1/3 times pi times the radius squared. Let's see, the radius squared is 3 squared times the height. And we get, or times the height, which is 2. 18 divided by 3 is 6 pi is my answer. And this is units cubed again. And I can substitute this into the calculator to get an answer. For the purpose of this video, I'm going to stop right there. When we rotate this same triangle around the y-axis, again, I have 2 and I have 3. Volume is equal to 1/3 times pi r squared h. So I substitute the values, 1/3 times pi times the radius here is 2. This is 2 squared times 3, and I get 4 pi. Again, this is a very different number, units cubed, than what I had before. I had 6 pi on this previous slide, 6 pi here, and now I'm getting the same triangle, just rotating it around a different axis, and I get 4 pi. This looks like it might be bigger, but you know what? Something is flatter, and it actually has a bigger volume. That's what's interesting about this. The last of these type of questions that was on the activity for today was to draw 0, 0, 3, 0, 3, 3, and 0, 5, and to rotate this figure. And I'm going to point out to you that this is a cylinder and a cone together. When we rotate it around the x-axis, go around the x-axis, 1, 2, 3, all the way over here. I should not do that. I should put it in its dotted line when it gets to the backside, like this. Dotted line around the backside. You can see it better when I draw the cone. Can you see that this is going to be like a silo, maybe? You look outside in the field, and there's a silo sitting there, so this is like a silo. And this is actually 2 problems in one, because we want to add the volume of the cone to the volume of the cylinder. So the volume of the cone, 1/3 pi r squared h, and this is going to be pi r squared h. Here my height is 3, this height is 2. In both cases, the radius is equal to 3. So when I substitute values, I get 1/3 times pi times the radius, which is 3 squared, times 2. Here we get pi times the radius squared, which is 3 squared, times the height, which is 3. So this becomes 1/3 times 3 times 3 times 2 is 6 pi, and this is 27 pi. What? Wow. Well, it's higher as well as it being same radius. So when you add this value to this one, you get 33 pi squared units. Or I mean cubic units, excuse me, because it's got a length, a width, and a height. It's got three different components. It's got the r times the h. Now back to our Desmos activity. This brings us to page, what is it, 19 or something, page 19. From 3 dimensions to 2. On the next 4 pages, there are some four three-dimensional figures, and you're supposed to draw the 2-dimensional figure that when rotated around the axis produces the solid of the rotation. And here's the first one. I'll make this a little bit smaller so we can see it. When I do this, I'm going to go on one side of the line because I want to rotate this around, and it goes something like this. I don't know if this is exactly right or not. Something like that. When you rotate it, can you see that you get this figure? Next, we have this cake, and let's see the cake. I'll start off like this. It goes down a little bit, goes down a little bit more, down a little bit more, and then it comes way out like that. When I rotate this around, I should get the cake. This one was one I think most students found easiest to do. The barbells was not as difficult as some of the others, but it was still a little bit more challenging. So we have something like that, and maybe something like this. I don't know if this is exactly right or not, but it's close. You rotate it around, you get this. The most difficult one by far was this. This is the bagel. People wanted to put it on the line, but I want to point out to you, if I were to take my bagel over here, I'll do it in a different color. If I were to rotate this around the axis here, and rotate this piece around, this is the half of the bagel. Can you see how it ends up being round like this? So here's the solution to those three. Which was most difficult? What would be the difference between rotating a two-dimensional figure that outlined the whole figure versus one that outlined only half the figure, and so forth? There's some questions for you to answer. And the lesson synthesis, today we're just rotating figures. Now, in the first one, it says to rotate this guy around the axis. I'll do this in a different color so you can see it. I rotate it around like this, and on here I have this solid, and this will be dashed, and you can see I get a cylinder. The one below it, though, this is more like the bagel that we just did. If I rotate this around, this is a hollow piece right here. And then if I go around like this, this is where it becomes solid. Going down. Here, go all the way around. And then this piece will be dashed because it's behind the solid piece that you can't see. Can you see how I get this cylinder minus the cylinder? That's kind of what we're looking at. Finally, there's this telescope problem. You're supposed to draw the figure that will, the two-dimensional half of it, when you rotate it, will end up with this. And I actually give you the solution for this on the sheet. And folks, I know this is a long video, but this was what we were doing today. It was volumes of rotation. Good luck and success.